All right, so in this video, we're gonna do a case example from the book, whether to do our production onshore or offshore, and to do this by using a decision tree. For Indara, we get that our demand is 100,000 panels each year or period, and our sell price is 70 euros. It stated that demand may increase by 20% with an 80% probability, and then decrease by 20% with a 20% probability. We also have for our onshore, we are going to produce in Europe, and offshore, we're going to produce in China. And then we get a value. We both have euros, and then we have Chinese yen. We are told that currently the exchange rate for the euro to yen is 9 yen equals 1 euro. We are told that and the yen's value is expected to rise by 10% with a 70% probability and drop by 10% with a 30% probability. This means that when the yen's value rises by 10%, it means then that our exchange rate would then decrease, meaning that we need less yen equals to 1 euro. If the yen's price drop, it means then that we have to increase the amount of yens to be valued the same as 1 euro. So for this one, it would be like if we say, for example, yen value expected to rise by 10%, let's say it goes into, it's worth 9 euros. No, 9 yen is equals 1 euro. This exchange rate would decrease. If the yen drops or its value drops, we will maybe see that then maybe 10 yen is equal to 1 euro. So this is maybe this is kind of, it's important to keep, to read and understand the question in the example, that the value of Ren is expected to rise and then drop, meaning that it will be the opposite for the exchange rate. We also get our discount rate, which is a 0.1, which we will use later. But with this data in mind, this one, we can then head over to our decision tree to find how this will happen. So here is my decision tree. This is for the onshore example. The decision tree will both be the same for both scenarios, either onshore or offshore. But there's different values we take into account for onshore offshore. So for my Indara here, I have D for demand and P is the price, or let's say for this case, the exchange rate, where we are told that the demand is 100,000 and then the exchange rate is 9. So 9 yen equals 1 euro. We were told that demand may be increased by 20% with an 80% probability. Like we have here, this one, the green one is increase. Demand is increasing by 80% and then decreasing by 20%. No, by 80% increase and then 20% decrease. And if it increases, it's 20%, or if it decreases, it's 20%. So for D here, for demand, we have our increase, which is 1.2 equals to then 120% increase, or not percent increase, but out of 100, so 20% increase. And then if it decreases, it's 0.8, so 20% decrease from the existing 100%. And the same thing here for our yen. As I said, the P is the exchange rate. So that's important. That's the exchange rate. So as I told before, if the yen's value rises, our exchange rate would then decrease. So it was a 70% chance that yen's value would increase, meaning our exchange rate would decrease. Therefore, we have it in red here for decrease. And it was a 30% probability for it to drop, meaning the exchange rate would then increase. So that's why we have 30 or 0.3% here. And it was the same that expect to rise 10% and then drop at 10%. So it's the same. Increase 10%, decrease 10%. So here I have done a finished decision tree, which is linked all together. It will always be the same for this when you have 3 periods or 2 periods in the future. So this would be period 0, period 1, and then period 2, so a total of 3 periods. So for period 1, we have the same data. There's nothing, the probability will not be taken into account. It's just our now values. And that would be the same for demand 100,000 and price would be 9, or the exchange rate. For this node, it splits out into 4 new nodes. Since we have 2 possible scenarios, demand and price both would increase or decrease. This one, the ØØ, which is increase. This one is ØS, which is increase, decrease, increase, and then decrease. So from these nodes, we have done that the price may increase or decrease, and the price may decrease and decrease, meaning that we have 4 different scenarios, or 4 different nodes that may happen in the future. So here we can see that both price and the exchange rate has increased. Here we can see that demand has increased while the price or exchange rate has decreased. Here it's decreased, and then demand is decreased, and then exchange rate has increased. And lastly, we have both that the demand has decreased and the exchange rate has decreased. So it splits off into 4 different nodes. From this split, it's important to know what the percentage of each node happening, or what the probability is for each node to happen. To find this probability, I have written it down here. Like for this node, it's 24%. For this node, it's 56%. For this node, it's 6%, and for the last one, it's 14%. Let's take, for example, this node. This was a decrease in demand, but an increase in price exchange. So a increase in D and a decrease in D and an increase in P. And to find this, we have to just multiply the percentage from what's happening. So this 6% is the same as we can find by doing our demand decreases. So 0.2 was the probability times the probability of our exchange rate increasing, which is 0.3. And then we find 0.06%, 0.06 or 6%. And we can do this from all of them. So for this one, it's 24%, where both P and D increases. And then we find the same way. We find the P increases and the D increases and the P increases. So that's how we find the percentage. And at the bottom here, I have just done a summarized each probability just to make sure that it's equal to 100%, because it has to be equal to 100% in total. So this was from the first period, so from our existing periods to the next period. And then lastly, we have for the next period after that. And as we see from the period 0 to period 1, we see that one node splits into 4 different nodes. And that's the same for this from period 1 to period 2. One node splits into 4 different nodes. So it would actually be 1, 4, and then 16 would actually be the amount of nodes. But as we can see here, many of the nodes for this one and this one, many of them have connecting probabilities. As you can see here, increase, decrease, and then decrease, increase would be the same as decrease, increase to increase, decrease. So it goes the same. That's why they are the same. But we can take this node, for example. We see here from this node, we have increase, 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 decrease, decrease, increase, and then we have this one, decrease, decrease. I think I said that right. I hope so. Yeah, it's the same, but this increase, 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 decrease, decrease, increase, decrease, decrease. That what is happening here would happen also for this node. So we can see from this one, it splits into 4 for the purple one, 4 different nodes where increase, 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 decrease, decrease, increase, decrease, decrease. So it will be the same. When we're looking from one period to the next, so from this period to this period, the probability for whatever is happening next from one cell or node would be the same as from the first period, as we can see here. So for this period would increase. If this cell splits off into 4, like we have here, 1, 2, 3, and 4 here, we know that this is increase, and increase, meaning that it will be the same probability, which is 24% for increase from this period to that period. So that's why it's important to keep track when we're going from one period to the other. The probability will be still the same. And then we can see this all down here. So many of them connect to each other. If you have 4 different 2 variables, this is how it will look like. Yeah, this is not that important. It's just to make sure that my probabilities are the right ones. So even though this one is wrong, it should be 0.14 and then percentage. This probability right here is just what that nodes from the first period would be. So it'd be like 24% for increase times 24%. So it would just, yeah. But that's not that important right now. But it's just important to make sure that you understand that from one period to the next and from the next period to the next one, it's the same probability for each split from that node. Yeah. So first one, this is our onshore example. On our onshore example, we find that we have a fixed cost of 1 million euros. Our variable cost is 40 euros per panel or whatever we produce. And then our plant capacity is 60,000 to 150,000 panels. And then I have done this here. I have added our capacity for 60,000 and 150,000. Our fixed cost is 1 million euros, and then our variable cost is 40 euros per panel. And then from this period, this is our second period, as you can see here, demand price, and then in the second period, which is this one. Since some of them you can see, this is just how I have set mine up to understand that they don't go in order, as you can see from the first node, from this one. You can see this. You see that it goes 1, 2, 3, and then it skips one node and then goes to the fifth one. So I've just added this to make sure, like this, and then skip one, and then this. And then we can see then that they're both from the second node, these two connect, as we can see here. The blue one and that one connect to that one. Not that important, it's just you can just disregard this sort of. It's just a total percentage for each nodes from the beginning. But then let's see here. We have our demand and price, which is also connected for each node. You can see it's the same, connected in order. And for this one is one node would be this one. And then for the next one, it would be this one, would be this one. So then, we have to see our total we have produced to start. Our demand is 144,000. Since our P is for the exchange rate for yen to euros, on our onshore example, we are not using yen at all, so we can sort of disregard the P in this example on onshore, but it will be highly relevant in the offshore example I will do later. So on our total bought or like total we have produced, we can see that our capacity is 60,000 to 150,000. So that's what we are able to produce onshore. We can see here that our lowest demand for possible demand is 64,000 and our highest is 144,000. So we already know that our demand is whatever we are able to produce. There's no limit in our production. And then we can do, as we can see here, total bought or total we have produced is here. And then our revenue would be then our demand, whatever we have produced, or the total we have produced times our revenue, or like what the sell price, which was 40 euros, 70 euros per panel. So this would be then 70 euros times 144. It's a different equation here and here. I will go later in it on the offshore when I do the offshore, because yeah, it's not relevant on the onshore. And then next one here we have our variable cost, or the cost it costs our cost to produce each panel. It's 40 euros for each panel, where we would then do like whatever we have produced, 144,000 times then 40, and we get this value. And then our fixed cost was 1 million euros. So I put 1 million here and then just drag it down for a fixed cost. So these two are the same. They can be the same, but yeah, disregard this. This is just the same. For our total cost, we just do our total cost in total, which is our variable cost and fixed cost in this example, which is for this node, it's 6,760,000 euros. Yeah, this is the same. So we disregard this. And then lastly, we just take our profit, take our revenue minus our total production cost or total costs in general, and then we find whatever we are sitting or whatever we have in profit. So this one, all of this was each node's probability for all of this. And then next one, we're going to do the first period, which is this one. And then we do exactly the same as before. We do our total produced, since it's in between still. See, our demand is still in between, meaning we can produce whatever our demand is. Our revenue, our variable cost, fixed cost, these two are still the same. And then we find our profit from that node. So for this equation, that's this probability. And then so forth. So for this one, that's third one, it will be for this one. And then we have to then now, since we are in our first period, we have to take into account what we were expected to earn for future periods, meaning these ones. So if we take the first node, we have our expected profit will be then whatever, this is this one. Let's see, sorry about that. We will see that because now we are here. And now we have to check, okay, how much are we expected from this node expected to earn in the future? If this node is happening, what are we expected to earn for future periods? So for the split, so for this node, this node, this node, and this one. And how we do this is that we take from the first node, as you can see here, that's why I have colored this in, so I know which node is connected to the first node. Same as we can see for the green one. We have the green ones here. So you see that these are connected here, because for the green it's these ones, this and this. Yeah, so what we have to do, we have to take what is from that node, what is the probability of this one happening? Well, it's, as I stated earlier, it's the same percentage, 24% for increase, which is this node, and then in brackets, and then take addition with the next node, this profit times its probability, plus then the second node, which is its probability, and then lastly the same one. So you have to keep, you're doing sort of this equation from this node. So you have to do from these two, this, and this. So it's the same thing as you do here. And then you find the expected profit for the future, or what you're expected to earn in the future without what you're earning right now for that first period. And then we have, as stated in our in data, we have a discount rate of 0.1, which is our K. And we know our formula for discount rate is 1 divided by 1 plus K. Which then would equal to, in this example, would be 1.1, since 0.1 plus 1 is equal to 1.1. And I have done this on a different like window on my Excel file. Disregard all this. This is just from another equation, but I've added this one here. So for this example, we have to then do our profit times or divided by 1.1 is actually what we are doing in this cell right here. So the profit, expected profit, taking into regard the probability of each profit happening in the future, and then divided by 1 plus the discount rate. So 1.1 is what it's actually saying here. And then we find our present value of expected profit of future periods. So that's the present value of that profit. And then lastly, we just have to find the present value of future expected profits, which is just adding what that node is expected to earn, if that is happening, plus whatever happened if that nodes happen and to the future, as we said here from these and this. So we just add these two together. And then you do exactly the same for every other node. You add what that node's values are, the same probability from each, because we're going from one period to the next one and not from the first one to the last one. Then we do the same here, the expected profit divided by 1.1, and then take these two together. And then lastly, on the first period, which we are now we are on this one. We just have to do exactly the same as we did before. Nothing has changed at all from this. So all of these are the same formulas, same everything. And then we have a profit of $2 million from this node. And then we have to do the same again. So instead of from this, when we were on the first period, we used the profits. But now we have to use the present value of future expected profits. So now we have to use these values instead of these when we're going from this to this, instead of going from this to this. So our expected profit now would be whatever we are expected to earn from each split times then the same percentage of this happening. And that's all the same, and we use the same discount rate. And then lastly, we just do the profit plus expected present value of future expected profits. And then lastly, we get to know that on the onshore example, or if production is in Europe, it would be 6,429,091 euros in profits, in expected profits. All right, let's head over to the offshore. This example is the offshore one. As I stated, the decision tree is the same. It's nothing changes on the decision tree. So we have done no changes here. The only changes we have for our offshore is that our fixed cost is 8 million yen, and our variable cost is 340 yen. And also our production plant has a capacity from 100,000 to 130,000. This means that we have a different currency we have to take into account, and also we have a different plant capacity that is important to take into account also. So I have done this here, capacity, fixed cost, and variable cost. As I stated here, 100,000 to 130,000, 8 million in yen. It's important to note that this is yen and not euros. So we can do as this. I think it's important if you do this exercise, it's important to use if it's in yen and if it's 100,000, it's or is in euros, just use the euros so we can better make sure that the value you have actually is in what currency. So right now this is why this example is kind of hard, because we have then restrictions on our capacity compared to our demand. So we can see here that for the third period, which is the same as the last one, we can see here that our demand is at the highest, is above our upper limit in production. And then we see also here that everything else is also in between or below. So none of these are above 100,000. That's why I've done this formula. It looks a lot worse than it actually is. So I will take you through it. This just checks that this is our lower limit and this is our upper limit for our production plant. And this is our demand, or what we want to produce. So I have this if formula. This checks that if our demand is higher or bigger than our upper limit, it checks that. So it checks if this one is higher than this one. And then I've stated if this is true, if our demand is higher than our upper limit, we are not allowed to produce more than 40,000, 130,000. And then if this is true, we will use the upper limit. So we will just use this one. And then lastly, if this is false, if it means that our demand is lower than 130,000, I have written now a new if equation for this one, if it value is false. Checking then if this demand is lower or higher than our lower limit. So for this equation, we have then our demand is bigger than our lowest limit. So if our demand is higher than a lower limit, we will use then our demand. If this is false, we will use the lower limit. So if this one is lower than this one, we will use this one. And then you can just take two parentheses. So this only does if this is false, it will use this one. And if this is true, it will use this one. So we don't take into regard this one. As we can see here, 64,000 is lower than 130,000. So therefore it uses this equation and it checks again. If it's higher than 100,000, this is false. It will still use the 100,000 because we can't produce anything lower than 100,000. And that's why we get it here. So this is the total we have produced. Our revenue is also taking into account what we have in demand, but also what we have produced. So I have this equation. It checks if our demand is higher than our what we have produced, which is this one. So if our demand is higher than what we have produced, then we will use what we have produced. If our demand is lower than what we have produced, we will use the value of the demand. So for this example, we have a 64,000 in demand, but we have produced 100,000. So therefore our demand is still 64,000. And then lastly, we just multiply this by the revenue or whatever we can sell it for, so which is 70 euros, as we can see here. Next, we have to do our variable cost. This is the same as before, the total we have produced times our variable cost or the cost for producing each panel. And this one is stated in yen. As you can see here, this is in euros, but this one is in yen. So this is the amount our variable cost in yen. And then we have 8 million yen in our fixed cost, which is the same here. And then I have added these both together in this column. You can just press insert and add another column and everything will shift away. So I have taken everything that is cost in yen here. So I get it together. And then now we have to convert whatever this amount is to the exchange rate. And that's why we have to take into account P, for this is our exchange rate for yen to euros. And to find this, we just have to do the total cost in yen divided by whatever the value of yen is to euros. So divide. And then we find for that node what the value is. And then we find the expected or the total cost in euros. And then simply we can just do the same again. Revenue minus our total cost in the same currency, which is the same. And then you do the same everything else. Everything else is the same as described before. No changes here. Yeah, so I'm not going to go over it all over again, but it's the same. So just, yeah. And then lastly, we get a present value of future expected profits in 6,247,497 euros. which is lower than what our onshore was, which was 6.4 million. So in this equation or this example, it was the right thing to do is to have it on onshore. So this is the answer. Right answer. Yeah, that was that question.